This video I want to talk a little bit about frequency response modeling, especially as it applies to measurement of the frequency response of the analog meter system that we're studying in the lab. In this week's lab study, we want to build an understanding for how model frequency response functions can be derived from transfer functions, and also, if need be, how we can experimentally measure frequency response functions of a dynamic system. And if we do measure them, we want to see if we can use that data to evaluate or to improve a theoretical model that we have in a frequency response form. When we talk about frequency response of a system, we're talking about a forced response, right? As opposed to, say, an initial condition response. And we're also interested in inputs to a system that might take a form such as a sinusoid that has a specific frequency that is either omega in terms of radians per second, or in the frequency can also be expressed in terms of hertz, right? So remember these expressions here: omega equals 2 pi f, and the frequency in hertz is also related to the period of a sinusoid, right? Study of systems, especially linear systems, although you can test a system this way, looking at the output given a certain sinusoidal input, even if it's not linear, but we're talking mostly about linear systems here. When you look at a linear system and you put in a sine wave, sinusoidal input with a certain frequency, omega, and amplitude u naught, and that's plotted here in the blue, when you look at the output after the transients die out, right, the output will have an amplitude y naught. It'll be at the same frequency, but it'll have some phase. So when we talk about phase, this is what we're talking about. We're talking about the phase difference between the input and output. And what we're interested also, because we know the output is a sinusoid, all we need to know is what is the ratio, say, y naught to the input u naught. Then we know everything we need to know about the response of the system, right? Because it's a sinusoid, and then all we need to know is the phase as well. And so those are the two functions that we want to measure, and we want to see how they vary as we vary omega. So theoretically, we can use a transfer function, theoretically, of a system to determine these frequency response functions. Now, a transfer function is defined as a relationship between two system variables, and it's a property of a system, right? So this transfer function I'm expressing here as TF is the ratio of the response, right, of the output to the input, and it's in the S domain. We call it either the Laplace or the S domain. We're no longer in the time domain, right? But now, the nice thing about a transfer function is that by setting this S operator equal to j omega, we can transform the S domain transfer function into a frequency response function. So now, instead of looking in the S domain, which is a bit abstract, we can look at what is going on as a function of frequency. So all we're doing is substituting S with j omega in these functions. We can then also express the frequency response function G here in polar notation by taking the magnitude and phase in this form here, right? Just blow that up a little bit, and you might recall that form. So what we want to look at is how can we derive these theoretically, and then we're going to look at how can we measure them as well. But first, what are these frequency response functions good for? Well, once we know an input, if we have a frequency response function, so if we have a G of j omega, say, both the magnitude and the phase, and remember the phase is also going to be a function of omega, then we can easily get that response. So all I need to know is this amplitude ratio and the phase. Why? Because to compute the amplitude, I simply take the magnitude of the input, U0, and multiply it by this value for the specific value of omega. And then I have the amplitude. If I want to know the phase, I can just substitute it into the phase function as well. So given any amplitude and phase functions, I basically know how the system is going to respond across all frequencies, right? And that's very valuable. So gaining insight into these frequency response functions is at least one of the reasons why we spend some time deriving theoretical transfer functions when we model dynamic systems. Now let's look at how we can derive them. Let's just consider the simple case of a first order system transfer function, and that takes this form here. It's just 1 over tau s plus 1 here, and this could represent many different types of linear first order systems where tau is the time constant, right? All we do is substitute s equal j omega, and we get in complex form the transfer function, but in frequency domain. So then all we do is compute amplitude and phase by taking the magnitude, which gives us 1 over square root of tau omega squared plus 1. And now keep in mind, this is just a number. All you need to do is substitute the parameter value here, the value of the frequency, and then you've got a single number at a certain frequency. And that, remember, gives you the amplitude ratio. Same thing for frequency. We can find the frequency for this complex number. In this case, we have 0 minus the angle of the denominator, and that's the arctan of the imaginary part divided by the real part. So at the end of the day, we get, for first order transfer function, negative arctangent of tau omega. And again, these can be plotted, and that's what I'll show you in a second, over frequency, right? We plot the phase, and we plot this amplitude function, right? And the first order systems have very characteristic response. The phase has a characteristic response, and so does the amplitude. Now with regard to plotting, a lot of times we plot the magnitude function here by taking the log, multiplying by 20, and that's defined as a decibel. Okay, so usually if you ever see a decibel unit, it's basically been scaled this way. It's just a classical way of doing this. That's related to a power ratio, but we won't worry about that at this point. But this is how you convert to decibels. Also, the phase angle is usually plotted in degrees. Also make note that the frequency sometimes may be in radians per second. Sometimes you might see in hertz. I put degrees here, and radians, I meant radians per second. Okay. Put a little example here. You can look at on the slides in more detail. A little RC filter. What does that look like? Well, that's just a circuit that has a resistor. And you'll remember this from your circuits class. If I put in a sine wave in here, right, and I can look at the output here. This is a capacitor resistor. For certain R and C values, right, here's your tau time constant. And here I'm just showing how you can plot. And this is and you can see I'm computing the magnitude ratio here and the phase. This is in degrees. This is in decibels. And remember, like for a first order system, how as you go higher in frequency out, it filters out. So what this means is that any signals that come in at these frequency range here are passed through. If any signals come in here, they're attenuated. So that's why we call this a filter, right? It filters out anything with frequencies out here. Very specifically introducing this example because we're going to possibly use this in the lab this coming week. But this shows you how frequency response is used and how they're plotted in particular. Just another example to show you. You can go back and look at the slides how you can take particular transfer function S domain. This just walks you through how you would come up with the amplitude and phase functions. Here's in the particular the transfer function that we derived, right, for the analog meter. This has the static gain that we measured, as well as the second order dynamics that we see for the analog meter because of the rotational inertia, also the spring, the rotational spring. You're going to have some dynamics that gives you a second order dynamics, and we derive this transfer function in the related video on modeling of the analog meter. So you can see all you do now is substitute S equals j omega here and compute your amplitude and phase functions. Now you've got a theoretical model for the frequency response functions of the analog meter. Here I've used R as the ratio of the forcing frequency to the natural frequency of the system. Now, we don't know any of these parameters. We've measured this parameter, but we don't have the damping ratio, and we don't have the undamped natural frequency. But we're going to see that if we can measure these functions in the lab, then we can match up by inserting recommended values or estimated values for damping ratio and natural frequency, and maybe fit our theoretical model to our experimental data, and in that way do what we call system identification. Just as a reminder, we call the DC gain if we have a theoretical transfer function and we make or omega, either S goes to 0 if you have a transfer function, or omega goes to 0 if you have the frequency response function. Here I made omega go to 0. Everything here goes to 0 except 1 on the bottom, so basically that's what we call your static gain. So like if you think of a frequency response function of some sort, this is omega. The value of the transfer function at 0, omega equal to 0, this is your static gain value there, okay, at low frequencies. Omega equal to 0 basically means, right, a DC voltage, because a DC voltage has a frequency of 0. So when you're not oscillating, when you just put a constant voltage, like you made all of your measurements in the first week of this lab, you were basically measuring static gain. Okay, so how do we go about measuring basically the ratio across different frequencies? Well, I hope you can see now we can do something that we call a swept-sine test. We make swept-sine measurements. So if we can take our system, and here's whatever system you have, and control the input, well, here I'm calling it X and Y, and basically put in a sinusoid, and you measure the sinusoidal output, measure the amplitudes, take the ratio of the amplitudes at every frequency, and so you're adjusting frequency here, right? Remember, it's a linear system, so the frequency will be the same here. Measure those, and so all you're doing is measuring these points across frequency. So you're sweeping the sine signal across different frequencies and making the G measurement and also the phi measurements, right? Different points, different frequencies. Very simple concept. Making these measurements can be tough. Amplitude, not so difficult. Phases can be tricky to measure. I want to show you a few examples before we close up. Here's a vibrational test on a cutting tool on a lathe. Sometimes you'll put a vibrational shaker on here, measure, say, this has what's called an impedance head. So you might be measuring the force in here and then maybe have an accelerometer also. Actually, an impedance head means that it measures at this point both velocity and force. So it actually measures the velocity over the force, and then you can plot that. So you're measuring a transfer function directly at this point for this system. And you can see it. This is showing plots over frequency. This is a frequency measurement. Now there's a vibrational example where you can see you have a rudder maybe on a ship, and you might actually put vibrational shaker here. You might have accelerometers placed on here, and what you're doing then is looking at different transfer functions, say transfer function between this acceleration and the point of excitation there. Very common type of analysis to do on things like rudders, aircraft wings, on vehicles and so on, to understand the vibrational modes. Finally, just to show you that there's a lot of different ways to get frequency responses, is an example I pulled out of this book on physiological systems, and it's showing both magnitude and phase functions for, and as I understand it, this is a pupil response to different types of light intensity. So you're actually, the output is motion of the pupil, or actually the area of the pupil, as incident light is on it. And so you can see they're doing the same thing that we've been talking about for different frequencies, making measurements across frequency of different amplitude ratios and phase response. You can see right here a table of the measurements that they made. So this whole concept of swept-sine testing, again, is used in a lot of different areas. Very valuable tool. So here's a recommended setup for you to use in the lab. As usual, we're going to use LabVIEW to control the MyDeck. In this case, we're using, remember, vision to measure the angular position, right, of the meter. So this is our output. Remember, we're making measurements of theta over voltage. So we want to put an input voltage here and measure theta. Now, you're going to learn how to use the analog output on the MyDeck. Now, that signal sometimes tends to be a little quantized. So remember, we talked about an RC filter earlier. An RC filter can filter that and make that a little bit smoother here. So you get a nicer sine wave in here, and you won't get so much jitter on this needle motion, and you'll get nice clean sine waves on the motion here. Remember, you want sine waves on output and input. So this is something that we may try for the first time. So this is something that we're going to try to do in the lab, to measure, rather to get a better input signal, which is the excitation, and hopefully also get better output signals. So in summary, again, transfer functions are input-output relations for a system model that can also be represented in the frequency domain. The latter here can be estimated experimentally, and that's what we're going to be doing in the lab using swept-sine testing. If we have a theoretical transfer function, we can compare the measured to the model and make judgments about our model, or we can also adjust key system parameters and adjust the model so that the model better fits what we measure. This is a way of doing what we call system identification.